Hey everyone, and welcome back for another deep dive. This time, we're taking a look at network theory.
Fascinating area.
It is, yeah. We've got a whole bunch of academic papers to dig through, so
Lots to unpack there.
yeah.
Yeah.
By the end, you'll be able to drop network controllability into casual conversation.
Absolutely.
And even impress your friends with some quantum physics trivia.
Oh, sounds fun.
So first things first, let's just, what even is a network?
You know, it sounds kind of technical, but honestly, a network is just a collection of things. We call them nodes.
Okay.
And the connections between them, those are the links.
So like on social media, each person's a node?
Exactly.
And their friends are the links.
Perfect example. You got it. And it's not just social media either.
Oh, so it's broader than that.
Way broader. These papers talk about social networks, yeah, but also biological networks, like how genes interact, even technological networks, things like power grids. It's really a powerful way to understand systems, no matter the field.
So it's a powerful tool for understanding. What can we actually do with that understanding, though?
Well, one thing we can do is try to control them. One paper dives into this whole concept of network controllability.
Okay.
It's all about figuring out how to steer these complex systems in a particular direction. Like, imagine trying to stop a disease from spreading, right?
Yeah.
Understanding network controllability could help you figure out who to target with information to, like, really limit the spread.
Oh, that's interesting. So you could see who's, like, the most influential in spreading the information.
Yeah, who are the key players in that network?
Okay. I get it.
Yeah.
I'm still a little stuck on, like, the basics here. The papers keep mentioning stuff like adjacency matrix, and it all sounds very, mathy.
It's actually pretty straightforward. Imagine a grid, right?
Okay.
Each row and column is a person in a group, let's say. If two people are friends, you put a 1 where their row and column meet. If not, it's a 0 up. That grid is the adjacency matrix. It's basically a code that shows you the network structure.
Ah, okay, so it's a visual representation.
Right.
But these networks aren't just frozen in time, are they? They're constantly changing, I imagine.
You got it. The papers highlight two main types of network dynamics. There's network change, and then there are relational events.
Okay, break that down for me. What's network change?
It's the, long-term evolution of connections.
Okay.
Think about, companies merging or countries forming alliances. That's network change. Big stuff.
So those are the big shifts. What about those relational events then?
Well, think of those as like the building blocks of those big changes. Sending an email, going to a conference together, even just having a casual conversation. Those are all relational events that shape the overall network over time.
So network change is the big picture, and relational events are all the little things.
Exactly.
That kind of lead to those bigger shifts.
Perfect. And what's really cool is that researchers have figured out what drives those dynamics. There are contextual factors like where you are or what you're into.
Makes sense.
Actor attributes, meaning things about you, like your personality or your skills even, and of course, relational factors.
So the relationships you already have affect the new ones you make.
Yeah, it's like a complex dance between external factors and individual choices. Super interesting to study.
That is really interesting. But I got to ask, why should we care about these network changes? What's the impact, like, in our daily lives?
Well, the studies show that network dynamics can affect, your job performance. For one, think about it. A salesperson with a huge network is probably going to do better than someone with 5 contacts. It's not just who you know.
It's how you're connected.
Exactly. The research also shows that a company's position in its industry's network can affect its market share.
So the same idea applies to businesses as well.
Absolutely. And, networks also affect innovation. A company with strong internal connections and open communication is more likely to be innovative, for example.
That makes sense. But the papers also talked about network dynamics and cognition. I'm not sure I followed that one.
It's pretty fascinating. Basically, changes in your networks can affect how you think and feel. Like if someone loses a lot of connections in their social network, they might feel isolated, and that can impact their well-being.
Makes sense. Wow, this really makes you think about all the invisible networks that shape our lives.
It really does.
But you ready to go even deeper down the rabbit hole here?
I think so.
Because the papers also touch on network theory in the quantum realm, which, honestly, that part's a little intimidating to me.
Yeah, it's pretty mind-bending stuff, but
Yeah.
stick with me. It might surprise you to learn that quantum mechanics and network theory actually have a lot in common.
Really?
Oh, yeah.
Okay, so quantum networks. Break it down for me.
Well, one of the key ideas is that networks can represent complex quantum states. It's like using a network as a blueprint for understanding the quantum world.
Okay, so we're talking about visualizing quantum mechanics with networks.
Got it.
I think I'm following, but an example would probably help.
Sure. Think of an atom. Now imagine a network where each node represents a different energy level of that atom.
Oh,
And the links show how those energy levels can transition to others. That network would be a visual representation of the atom's possible quantum states.
okay, so we're using networks to represent something that's normally really abstract. That's wild. So what other connections are there between networks and the quantum world?
Well, one of the most fascinating aspects is quantum entanglement.
Oh yeah, the spooky action at a distance.
Exactly. And what's really interesting is that networks can help us understand and even manipulate those entangled connections.
Hold on. I need you to slow down for a second there. Can you give me an example of how a network facilitates entanglement?
Imagine a network where each node is a qubit. Okay.
Which is like the quantum version of a bit in a computer.
Okay, yeah.
Now, some of those qubits are entangled, meaning their fates are linked no matter how far apart they are.
Right, like they're connected by some invisible thread.
Exactly. The network structure can determine how easily that entanglement can be spread and used for things like quantum communication or computation.
So the network is like a highway for entanglement.
You got it. It allows it to travel between these distant qubits.
This is blowing my mind. But this all feels very theoretical. Are there, like, actual physical quantum networks being built?
There are. It's early days.
Yeah.
But scientists all over the world are working on building them. And these networks could revolutionize communication, computing, even sensing. One of the most promising applications is quantum key distribution, or QKD.
QKD.
Yeah, it uses quantum mechanics to create encryption keys that are basically impossible to crack.
Unbreakable encryption. Sounds like something in a spy movie.
It does, doesn't it? But it's real. QKD networks are already being tested in several countries. Wow, so this isn't just theory anymore. It's actually happening.
It is. Pretty exciting stuff.
Yeah, that is pretty incredible. It seems like networks aren't just a tool for understanding complex systems. They're also a key to unlocking the potential of these quantum technologies.
Wow. I think we need a minute to process all of this.
Yeah, take a breath. It's a lot to digest. But before we do that, I want to leave you with a question to ponder. What other complex systems in your own life might be better understood through this network lens?
We're back, and my brain is still buzzing from those quantum networks. It's crazy to think that these invisible connections could, like, change the future of technology as we know it.
It is a huge shift. It's like we're going from this world of separate systems to a world where everything's linked, even down at the quantum level.
Before we went to that question, you mentioned QKD, that quantum key distribution. That sounds like something straight out of, like, a science fiction movie, but you're saying it's a real thing. Oh, it's definitely real. QKD uses these principles of quantum mechanics to create encryption keys that are, like, theoretically impossible to break. And it all comes down to the fact that when you measure a quantum system, you inevitably change it. So if someone tries to sneak a peek at the key, they'll leave a trace and the people using it will know.
So it's like having a built-in alarm system for the encryption itself. That's amazing. But how does this actually work? Are we sending entangled particles through fiber optic cables or something?
You're on the right track. One common way to do it is the sender encodes the information onto photons. Those are the fundamental particles of light, and then they send them to the receiver.
Okay.
And then they use these quantum properties of the photons to establish a shared secret key.
It's kind of mind-blowing. So we're using this weirdness of quantum mechanics to, actually secure our communications.
Exactly. And the cool part is QKD networks are already being used in different parts of the world. For example, China's got this fiber optic network. It's over 2,000 kilometers long, and they're using QKD to protect government and financial stuff.
So this isn't just theoretical anymore. Quantum networks are having a real impact.
They are. It's really exciting.
It is. But I have to ask, are there any limitations to this QKD thing?
Yeah, there are. Distance is a big one. Quantum signals, they tend to weaken over long distances because of loss and noise in those fiber optic cables. So right now, QKD systems are limited to a few hundred kilometers.
So no beaming entangled photons across the globe just yet?
Not yet. But scientists are working on it. One promising approach is using quantum repeaters.
Quantum repeaters.
Yeah, they can amplify and clean up the quantum signals so they can travel further without losing their, fidelity.
It's like having these rest stops for entangled photons,
Yeah.
helping them on their journey across the network. So cool. What other challenges are researchers facing in building this global quantum internet everyone's talking about?
Building a global quantum internet is a huge GE task. One of the big ones is developing good quantum memories.
Quantum memories, what are those?
These are devices that can store quantum information for a long time,
Okay.
which is really important for things like quantum repeaters and doing complex quantum calculations.
So they're a key piece of the puzzle for unlocking the full potential of these quantum networks.
Exactly.
What are some of the ways people are trying to create these memories?
Well, there are several promising approaches. One way is trapping single atoms or ions in electromagnetic fields. Then you can control their quantum states.
Okay.
Another approach is using these defects in diamond crystals. They can actually show quantum properties at room temperature. Pretty wild. And of course, there's also a lot of research into using superconducting circuits. Those can store and manipulate quantum information, but only at super low temperatures.
Sounds like there's a whole universe of possibilities and challenges in developing those quantum memories. So besides QKD, what other potential applications are there for these quantum networks?
Oh, so many. Imagine a world where we could do distributed quantum computing. Multiple quantum computers all linked up through a network, working together to solve problems that are just too hard for our regular computers.
So we're talking about like a quantum supercomputer.
Yeah.
What kind of problems could we even solve with something like that?
It's hard to even imagine. We could make huge leaps forward in areas like drug discovery, material science, maybe even artificial intelligence. Imagine simulating complex molecules with perfect accuracy.
Yeah.
That could lead to new drugs, new materials, all sorts of stuff. We could even come up with new algorithms for machine learning that could revolutionize things like image recognition, natural language processing, you name it.
Sounds like quantum networks could be a game changer for so many fields.
It really does.
But I can't help but wonder about the downsides. Should we be worried about the ethical side of things? Or the impact on society?
It's always smart to think about the consequences of any new tech, especially something as powerful as quantum networks. But it's also important to be balanced in our approach, too.
What kind of concerns have people brought up?
One big concern is that this tech could be misused for things like surveillance and invading people's privacy. If quantum computers get strong enough to break our current encryption, it could be a big problem for national security and individual privacy.
That's a scary thought. The same tech that could revolutionize cybersecurity could also create new threats.
Right. It's really important to come up with ethical guidelines and regulations to make sure these quantum technologies are used responsibly and for the good of everyone.
Makes sense. What about access to this technology? Will it be available to everyone, or will it just make the digital divide even worse?
That's a really important point. We need to make sure everyone benefits from these quantum technologies, not just a select few.
Right.
That means investing in education, infrastructure, and policies that promote inclusivity.
This is all so fascinating and complex. Maybe we need a moment to reflect on all these implications before we move on.
I agree. It's important to have these conversations about the future of quantum networks and what it means for our world.
And we're back. Still thinking about those quantum networks.
Yeah.
It's crazy to think that they could change, everything about technology.
Yeah, it's definitely a paradigm shift, moving from isolated systems to, a world where everything's linked up, even at the quantum level. It's pretty amazing.
You know, it's funny. We've been talking about these physical networks, right? Like the fiber optic cables, the quantum computers, the entangled particles. But earlier we were talking about networks more broadly, as a way of seeing and understanding complex systems in general. How does that bigger picture thinking apply to the quantum world?
That's a great point. A network is just a way to show the relationships between things.
Right.
And in the quantum world, those things could be particles, energy levels, even, abstract ideas like quantum states.
So instead of thinking about quantum mechanics with all those equations and abstract concepts, we can visualize it as a network, nodes and links representing those different elements and how they interact.
Exactly. One of the papers actually talks about this idea of representing a molecule as a network.
Okay.
So the atoms would be the nodes, and the chemical bonds between them would be the links. That network would give you new insights into the molecule's properties and how it behaves.
So we can use the language of networks to, unlock the secrets of the quantum world. That's pretty cool. Are there other examples of how researchers are using this approach?
Absolutely. One really exciting area is the study of quantum entanglement through network theory. Researchers are using networks to model how entanglement is distributed and controlled in big systems of qubits.
So not just understanding entanglement, but like controlling it, engineering it for specific things.
Precisely.
Yeah.
If you design the network in a smart way, you can manipulate how entanglement flows, directing it where you want it to go, protecting it from noise and decoherence, which is when that quantum state kind of breaks down.
Wow, that's amazing. But at the end of the day, why does this all matter? Why should our listeners care about network theory, whether it's applied to like our social lives, biology, or even this crazy quantum realm?
It's a good question, and I think the answer is that network theory gives us these powerful tools to understand and deal with our increasingly complex world.
That's like a new way of seeing, a new way of thinking, right?
Exactly. And as our world becomes even more connected, that ability to think in terms of networks, to understand those complex systems, it's only going to become more important.
So what's the takeaway message for our listeners today? What do we hope they've gotten out of this deep dive into network theory?
Well, I hope we've made them curious. I hope they'll start looking for the networks in their own lives, in their work, in their communities. I hope they'll think about the world in new ways, see those connections, the things that depend on each other, the hidden patterns that shape our reality.
That's a great way to put it. I think this deep dive has shown us that networks aren't just some abstract concept. They're a fundamental part of how our world works. From the everyday interactions we have with each other to the mind-blowing potential of these quantum networks. The connections are everywhere. So keep exploring those connections, keep connecting the dots, and stay tuned for more deep dives into the amazing world of science and ideas. Until next time, happy networking.